Good morning, I'm Nick Conlan from Apex Acoustics, and I'm presenting our paper which looks at the empirical relationships between Lnight, or the time averaged 8-hour levels, and Lmax levels due to single noise events. There is a general consensus that assessing the effects of noise on sleep should include a consideration of individual noise events, as well as the time average noise levels over a nighttime period. And many studies have shown that the clear exposure relationships between the maximum levels of individual events and impacts during sleep. Recent guidance supports that approach, where LAF max levels are normally assessed for new residential developments which are exposed to transportation noise sources. However, the typical relationship between the time averaged ambient noise levels and the noise from single events is not widely reported or known. Understanding the potential uncertainty from LAF maximum measurements is becoming more important as validation measurements for residential buildings is becoming more common prior to occupation, and the risks of measurements during a potential noisier night should be understood and accounted for within the facade design. If we start by looking at some of the current guidance, the 1999 WHO guidelines for community noise state that if the noise is not continuous, sleep disturbance correlates best with LA max, and effects have been observed at 45 dB or less. This is particularly true if the background levels are low, and noise events exceeding 45 dBA should therefore be limited if possible. That approach is still relevant, and the most recent guidance in ProPG states that in most circumstances in noise-sensitive rooms at night, good acoustic design can be used so that individual noise events do not normally exceed 45 decibels LAF max more than 10 times a night. However, where it's not practicable to achieve this guideline, then the judgment of acceptability will depend not only on the maximum noise levels, but also on factors such as source, number, distribution, predictability, and regularity of the noise events. And by saying that, really, it offers the opportunity to put forward a bespoke assessment, because clearly having 7, 8 or 9 loud events and then a big drop to the 10th doesn't mean you should just ignore the higher values. But that really is getting into the realms of how to assess maximums, which is really beyond the scope of this paper. And even more recently than the ProPG, there is reference in the AVO guide that single events should not exceed 65 dB LAF max when controlling overheating. So that would normally be when windows are open. And that is based on the single highest maximum, which also brings with it the most uncertainty, although you will find that out later. For the non-overheating condition, the AVO guide refers to the 10th highest maximum as per the ProPG guidance. I undertook a literature search on information available on variation of maximum levels, and there's a very relevant document called A Good Practice Guide on the sources and magnitude of uncertainty arising in the practical measurement of environmental noise. The Good Practice Guide provides details of potential areas of uncertainty, and for this assessment, the measurement location where we compare consecutive nights is constant for each position, and so the likely areas of uncertainty between the consecutive nights will be due to the noise source, as in variation of traffic flows and types of vehicles, and also the transmission path, so different weather conditions, particularly wind direction, wind speed, and potentially variation of wet or dry road surfaces. The guide also includes a case study which refers to a lecture entitled Designing Outdoor Sound Measures by Ian Findle. The lecture compares sampling strategies for the estimation of annual indicators of road traffic noise, the LA EQ for 24 hours, with the probability of being within 1 dB of the annual average as shown in the table. So for a single day's measurement, which is quite common, I'd say, for most people's assessments, it suggests a 35% probability of being within 1 dB of the annual average. 2018 WHO Environmental Noise Guidelines also include some useful information on maximum levels. One of the studies referred to in the WHO review measured both slow and fast response maximum levels, and the differences between the two metrics are shown in the table. The systematic review includes a review of studies on noise-induced awakenings published since the year 2000, and although the evidence for awakenings was not considered strong enough for inclusion in the eventual WHO guidelines, exposure response curves are presented for road, rail and aircraft, which have been derived from the raw data from 2 large field studies. And for most situations, the fast weighted maximum would be around a dB more than the slow weighted maximum, or certainly the mean is less than 1 dB. Surveys we selected for the data analysis included measurements undertaken by Apex since 2015 that included at least 2 consecutive nighttime periods. That provided us with data for 289 separate measurement locations from 139 separate projects. When we did an initial comparison between the nights, and where the Lnight between separate sets of measurements varied by more than 3 dB, the data was omitted if the variation was due to different weather conditions, measurements that were done over a weekend, or where measurements were dominated by plant or entertainment noise. And once we discarded those measurements, we ended up with a final data set of 478 nighttime measurements, which is taken from 239 separate measurement locations. All measurements were recorded at 1 second intervals, and they were analysed to calculate the parameters that are listed in the table for each whole night survey period. The initial concept was to look at variations for different land uses, such as urban, suburban and rural, in a similar way to the DEFRA National Noise Incidence Study. However, when the survey locations were reviewed, it was clear that there were very few rural locations, probably because they didn't need assessing, and it was difficult really to differentiate between what you'd consider to be urban and suburban. And therefore really we consider that all of the measurements that are used are representative of locations that could have residential developments and are exposed to transportation noise. It's presented graphically as box and whisper plots without outliers. The box part covers the interquartile range, and the centre line in the box is the median value. The upper line of the box is the 25th percentile and the lower is the 75th. The whisker part is calculated based on the formula shown, and they're sometimes shown as typical maximum and minimum values, although there are some outliers which are not shown in our images. So it doesn't represent the extremes of all data, but the mean and standard deviations are provided in the paper if you do want to do some further analysis. So here is the comparison of the parameters from 2 consecutive nights at the same location, and it's based on 239 pairs of measurements. We've made comparisons for the Lnight value, the single highest maximum for each night, and the 10th highest maximum for each night, based on 1-minute sampling periods. This comparison is to enable an estimate to be made of how each parameter may change if it were to be repeated for a different day. The variation in the Lnight values, which is shown on the left, was generally less than 1 dB for more than 50% of the measurements. Almost all were within plus or minus 3 dB. The comparison between the 10th highest maximum, which is shown on the right, was not much different, with over 55% within plus or minus 1.5 dB. But it had a wider range overall, and almost all of the measurements were within plus or minus 5 dB between the 2 consecutive nights. And I think, as you'd expect, the greatest variation occurred for the single highest value, which is the centre graph, where 50% of the measurements were greater than 3.5 dB difference between the consecutive days. On this basis, the uncertainty from a single night's measurements may be acceptable for the assessment if a tolerance of about 2 dB is added to the Lnight and the 10th highest Lmax. But an assessment based on a single highest maximum, I think you'd need either to have a much larger tolerance or undertake measurements over several different nights. The next comparison is between the time averaged Lnight and the single and 10th highest maximum levels during the same night. The importance of this comparison is to establish if maximum noise levels are likely to drive the design of the facade. We know that maximums need to be considered, but what I was never really sure about was if they were always important. So for the comparison on the right, which is between the Lnight and the 10th highest maximum, the median difference is about 18 dB, and for more than 75% of the measurements, the difference is more than 16 dB. So if we consider the normal criteria applied for bedrooms, where the time averaged Lnight criteria is 30 dB, the criteria for the 10th highest max is taken as 45, then the difference between the two is 15 dB. So as you can see, for most of the time, the Lmax is the more important parameter. For the comparison on the left, if we were to follow the guidance from the AVO guide, the upper limits for occasional opening of windows can be 42 dB Lnight as a time average value and 65 dB LAF max for the single highest event, and for that we have a difference of 23 dB. So again, we can see more than 75% of the measurements have a difference of more than 23 dB between the time averaged and single highest maximum. So again, it's more than likely that the maximum level will be the most important parameter. The final comparison looks at the variation of the 10th highest maximum for different time logging periods. Previous studies have concluded a time period of between 1 and 3 minutes to be appropriate for assessing maximum levels and sleep disturbance. Therefore, it's useful to understand the uncertainty should the only available data be for longer periods. And clearly the choice of time interval length will significantly affect the number of maximum levels used in the assessment. So if we've got 1 minute time intervals, then we have 480 separate maximums. If it's 5 minutes, then it's 96. And if it's 15 minutes, then it's only 32 separate maximums. The variation between the 1 minute time interval and 5 minute time intervals is shown on the left. And for over 25% of nearly 500 measurements, there was no difference for the 10th highest value. And for over 75%, the difference was less than 1 dB, which I found fairly surprising, and it indicates really that the maximum events are fairly well spread out. As you'd expect, the comparison with the 15-minute values, as shown on the right, has a larger range, and about 50% of measurements, the median value is shown around 1 dB difference, and 75% is just over 2 dB difference. So even if you only have 15-minute data, a correction of sort of 2 to 3 dB should be sufficient to estimate the 10th highest maximum relating to sleep awakenings. And so our conclusions. The analysis has been based on 478 separate nighttime measurements. Single events will influence the facade design for the majority of projects, and yet the maximum levels have the greatest level of uncertainty between different nights, and significantly greater uncertainty when you're looking at single highest levels compared to the 10th highest. And finally, for time logging periods of 5 minutes, surprisingly similar to the 10th highest from 1 minute logging periods, and a 1 dB correction is probably sufficient between the two. And if you only have 15-minute logging periods, then a 2 to 3 dB allowance should be added to the 10th highest maximum when assessing sleep disturbance. So that's the end of my talk. Thank you. If there's any questions.